Hey guys, this is Akash. I'm a third year undergraduate here at IIT Bombay and I'm the manager of the Cybersecurity Club. I'm back with a second video on binary exploitation, and this time we'll do some advanced stuff. So let's begin. Last time we talked about how we can jump to a malicious function using our inputs and get some malicious code executed. But what if we don't have a function we can return to? Why would anyone put a malicious function in their code? So what do you do then? You still need to get things executed. You need to get some code or instructions, what they call executed. So you need to insert it somehow into the binary onto the memory so that it can get executed. So you can't, but you can't just input C code or whatever language the program was written in, because your input, it goes onto the memory. So memory is just bits, ones and zeros, and that's what the computer interprets. It will not see your code as it will not interpret your code directly. There are encodings, and your code gets compiled by the compiler into assembly code and then machine code. So the machine code goes onto the memory. So what you need to do is you need to send directly send the machine code of whatever instructions you want to get executed onto the memory. So how that is done is you first write assembly code, which depends on what computer or what format the binary is, or what machine you are running it on. And that is learning assembly is a task in itself. So you won't really want to learn it for doing shellcode exploits. I mean, it obviously helps because you'll get to write more advanced exploits and know exactly how they are working. But if you don't need to learn it initially when you are beginning with this. So but you somehow need the assembly code, right? So what do you do? So we have this website called shellstorm.org, and so they have a big database of shellcodes right here. So what a shellcode is? Shellcode is the machine code I was talking about. So this is what gets loaded into the memory. These are the bytes the computer can interpret as ones and zeros as instructions. So I have one open right here, which gets us to our ultimate goal, /bin/sh, get a shell onto the other person's computer, or get a root shell somehow. So exec we call what's called a system call, which executes whatever string you pass to it. So /bin/sh runs the sh binary in the /bin folder, and then which basically gives you the shell. So this is the final shell code which you are going to pass on to the memory and pass into your exploit. But let's see how this came about. So this is exactly what we see here, 31C050 and stuff. So I'll go through this assembly code, and since we studied about the memory layout in C in the last video, you'll be able to relate things to that a bit. So initially what we do is we XOR EAX with itself, and XORing two numbers with itself gives 0, and which is stored in the EX. So EAX is actually a register. Register is some amount of memory which is stored directly on the CPU. It's present on the CPU, on the processor. So EAX specifically is stores 4 bytes of data. So yeah, we're first putting EAX 0 into EAX, and then we are pushing EAX onto the stack. Pushing it onto the stack, basically now your stack has a null byte, or 4 null bytes basically. And then we push these kind of cryptic looking hex strings there. So these are not really cryptic. This is just a hex of the command you want to get executed. So I have this hex to ASCII converter here, and I've copied these values, and what this converts to is hs//niv/. So what does that mean? What is hs//niv/? So there's a concept of endianness in various architectures. So what you see here is data stored in the little endian format. What that means is the 4 bytes, they are stored in an opposite order basically. So the first byte is stored at the end. So what this really turns into or reads as is /bin//sh. So this is /bin//sh binary, which will give you the shell, or which this is the argument you want to pass to the execv function. So by the way, we have a double slash here just to avoid any null bytes at the end, so or anywhere in the shellcode. So yeah, that's so you don't want null bytes in the shellcode, because your input is getting copied. A lot of times your input gets copied, and the string copy functions, they stop on the null byte. A lot of string functions in the C library, they stop at a null byte, so you don't really want to have null bytes in your shellcode. Yes, that's something to be careful about. So we push the value on the stack. So and now we move the ESP, which is the stack pointer. So the stack pointer points to the bottom of the stack basically. So we pushed EAX, and then we pushed /bin/sh onto the stack. So the ESP is now pointing to /bin/sh, and now we move the value, basically the pointer, to /bin/sh string to EBX, and this EBX acts as an argument of the execv function. So yeah, that's by convention that the execv takes the pointer in EBX as the argument. So you can see all the syscalls. You can Google about all the syscalls, and you'll get what register corresponds to what arguments. And then we ECX, EDX, we move 0. So these are the other 2 arguments which are passed to execv, which are environment variables and so different stuff. Basically we are passing null there. We just need 1 argument for getting execv /bin/sh executed. So what we then do is we move B into AL. So hex B is 11. 11 is the integer identifier given to the execv system call. So and AL is the least significant byte of EAX. So EAX was 4 bytes, and the least significant 1 byte is referred to as AL. So moving B into AL basically sets the value of AL to 11, or the value of EAX to 11, because the rest of the bytes are 0. So you must be thinking why we moved B into AL, and why not move it directly into EAX. So the reason is that will probably result in null bytes in the shellcode here, because 0xb is in 4 bytes. It's actually 00000 and then B. So you'll get 3 null bytes in the shellcode. So to avoid that, you move B into AL. So yeah, and then you're calling the 0x80 interrupt. So what this interrupt does, it reads the value from EAX, and which is B here, and identifies what system call you're calling. So yeah, that's internals into the operating system. Yeah, you need not get into those, but yeah, that's how it works. So and then it'll read the arguments from EBX, ECX and stuff, and basically yeah, execute execv /bin/sh, which is what you finally want. So here is also a C code which will execute this. This is just an example. This has nothing to do with our exploit, but you put your code in you put the machine code in array of characters. and then you convert it into a function pointer, and then you call it. So it's just like a function call, and this thing will start getting executed one at a time, and they'll be interpreted as these instructions. So going back to the presentation. So yeah, now after we have the shellcode, we have to somehow put the shellcode into the memory, right? We have the instructions or the machine code we want to get executed, but how do you get it executed? You have to place it somewhere in the memory, and then you need to get your the function to jump to it, or your pointer to jump to it, so that it can get executed. So one way to put it in the memory is to pass it into a buffer. As we were doing buffer overflow exploits, and we can pass this shellcode into a buffer, and so to return to it, we'll need to know the address of the buffer. Another way to do is to pass it into an environment variable. So if you run env on your terminal on shell, you'll see a lot of environment variables basically set, which work in the background. They're used by various programs to get certain information about your machine, what kind of settings or configuration you have for your machine, and do stuff based on that. So these environment variables also get loaded onto the stack before before your binary starts running, before the code starts running. This is a simple example. Main is calling the vulnerable function. It just has one buffer, and then it's doing getS on the buffer. So as you know, the problem with getS is it doesn't really check how many bytes the user is entering. So even though the maximum is 64 bytes, it's still, it doesn't limit you. You can input any number of bytes there, and it'll basically just overflow the rest of the stuff if you enter more than 64 bytes. So yeah, never use getS in your functions, and most of the compilers will really give you a warning if you use getS. So yeah, so this is bad code, and hence it's getting exploited. So yeah, what we saw last time, the main calls the vulnerable function, and how the stack is set up is you first pass the return address, which is address back to the main, and then you have the base pointer for main stored here, so that when you return to the main, you can restore the value of EBP, the base register, base point containing the base pointer. And then you have the 64 byte buffer. In this first example, what you do is you pass the shellcode so the input here is shown as if the shellcode has to be 64 bytes, but yeah, that's not really necessary. It can be anywhere inside the 64 plus 4. So at max you have 68 bytes to pass. Your shellcode has to be at max 68 bytes, because the next thing has to be the address of the buffer. If you override the return address with your shellcode, then yeah, that would be really problematic, because it won't really jump back to your shellcode, which is what you want. And most of the shellcode, the one we saw, at least it easily fits into 68 bytes. So yeah, that's not a problem. The next way is using environment variables. So before running the program, what you do is you have an environment variable. You set an environment variable, and here they called it egg. You can call it anything, but yeah, you put an egg, and when you jump to it, you can say you hashed the egg, and it had code inside it, and it got executed and stuff. Yeah. So what you do is you set the value of egg, and you pass your shellcode here. It can be very long or whatever. You don't need to limit yourself here like you had to do in case of a buffer in which you were limited to 68 bytes, and here you can pass any amount of gibberish, and then basically the return address has to be the address of the environment variable, since you want to jump there. instead of main, you'll jump to your shellcode and execute it. So, I mean, this sounds easy. You just have to overwrite an address, but it's not really that simple to get the address of wherever you put the variable. One reason for it is, or one protection which is employed against getting this address easily, is what is known as ASLR, which is address space layout randomization. So every time you run your binary, it gets loaded at a different place in the memory, so at a different address. So if you have if you somehow figured out that this in this run the shellcode is loaded here, and then you want to exploit it in the next run, if you pass this pointer, it will not really jump to your shellcode. It will jump somewhere else because actually your shellcode has moved. It got loaded somewhere else in this run, and that's one mechanism they use to avoid such kind of attacks. So what do you do about it? I mean, hackers don't stop, right? So we don't exactly know where our shellcode is. So what we do is we use what is called a NOP sled. So what a NOP is it's a short for no operation. Basically, it's an instruction but doesn't do anything. So basically what you'll do is you'll keep a lot of no operations or NOPs before your shellcode. Say you have 1,000,000 NOPs before your shellcode, and then you have your shellcode. So if you jump anywhere inside that, it'll basically jump one by. So a NOP does nothing. It just jumps to the next one, just jumps to the next byte, jumps to the next byte, execute next. It keeps jumping till it'll keep jumping until you get to the shellcode. So basically now you don't have to jump to an exact address of the shellcode. If you jump anywhere in the 1,000,000 address, 1,000,000 bytes, you'll eventually get there. You'll eventually get to the shellcode, and it'll get executed. So yeah, you don't need to know the exact address, but you need to have some kind of idea around what place could it be, and you generally be able to make multiple guesses. So yeah, the probability of you to get this right depends on the amount of guesses you have and the length of the NOP sled. It's called a NOP sled, basically. It's like a sled, you keep sliding along it. So yeah, you put a lot of NOPs right before your shellcode, and you can use anything else which doesn't have any effect. So this is exactly what I explained. You can be imprecise with your returning, and then you finally get to your shellcode, and then all the instructions get executed, so they are good to go. So that was shellcode injections. Now we see, so overflowing buffer seemed very easy, right? So, and it's these exploits happen a lot, the buffer overflow, and due to bad coding, these exploits are very common. These bugs are very common where they don't check the position of or the length of your input and stuff. So how do you protect against this? So this is without any stack protection. This is just a normal stack. There's a normal example which we saw in the first video actually. So you have a bad function, its address, you just jump there, you overwrite the return address with the address of the bad function, and you jump there, so and you get some malicious code execution. So that's the normal case. So what do you do to avoid it? Also, as you see, you have to overwrite this entire thing before you get to the return address, and then you overwrite the return address, right? So this means that whatever you had in this portion of the memory also gets overwritten with some gibberish. So how to avoid this? We have a concept of something called stack canaries, and all the compilers these days they use this by default. And what it does is, for every function the compiler sets a stack canary at the beginning. So when the function is called a random, after the return address, that is between the return address and the EBP, you have a canary stored. A canary is basically just a random value which is generated, and then you store it in between these things. So if you want to override the return address, you have to override the canary first. There's no way to skip this part and override this, because your buffer starts from here. You have to override the canary. So the concept is basically you override the canary. You don't know the value of the canary, and when the function is going to return, it will actually check the value of the canary. It will match it with a global value which it has stored in some other part of the memory. It will match it with it, and if the values don't match, it will crash, it will abort, it will give you an error, but it will not jump to your shellcode. It will not jump to the wherever you wanted it to jump. So how do you bypass these? Of course, these are there, but still we see a lot of exploits these days, and so of course there are ways to bypass this, but they're not usually that easy. It's not usually easy to get the value of the stack canary. One simple way to do it, not really that simple, but the basic idea to do it is, you don't really know the value of the stack canary. What the protection relies on is you not knowing that random value, because it's generated on every run of the binary. So you have to somehow read that value. You somehow have to know that value. So you have to find a way of reading value from the stack. It has to be you have to find some way around, some exploit in the binary which will help you read some values from the stack. Then of course you read the value of the canary, and then when you're overwriting the return address, you also override the canary, but this time you overwrite it with the correct value because you had already read it from the stack. So say before the getS, you somehow had some more code, or you could somehow get some malicious code execution by which you could read the canary and print it out, and then when you print it out, you can pass it to the getS function when it asks for an input. And so you'll basically override the correct value of the canary, and then when the compiler, or when it is checked at the end of the vulnerable function, it will say this is the right value, so there are no buffer overflows, but it will return to the wrong address, or according to us, the right address. So that's almost all for this video, but I already told you about this resource for getting the shellcodes, and it has multiple shellcodes for doing the same thing. You can try out multiple of them if one doesn't work out on your computer. And then another thing is, you might want to read this, or you might want to wait for another video on this. So this is something called return oriented programming. So the shellcode injection we talked about, it's not, so there are protections against those where you don't allow the user input to be executed. So what do you do then? You have to use something called return oriented programming, where it's an interesting concept where you stitch code from various parts of the memory, from libraries, from the user code, and wherever basically you can find code which will help you do what you want to in the end, and you stitch various sections of the code and somehow get it run. It's very beautiful, and you will see it in the next video. So let's do a demo for shellcode injection we talked about. I have Kali Linux running here, and so I'm running as the user Akash, so that we can see here through my ID group, whatever UID, GID, etc. So we have a file in this directory called vuln, which is So yeah, here we see the permissions of this binary. It has the S bit, which is the set UID bit, as 1. Basically the set UID bit is set. So what that means is whoever is the owner of this binary, which is the root in this case, whatever we do is executed as that user. Yeah, so if you can get this binary to do stuff which do some stuff, it will get executed as root. If you get it to run an exec/bin/sh, it will give you a root shell, and then that's the ultimate goal. So yeah, that this is also a bad practice to keep binaries with set UID bit set. You might want to do in some cases for some specific users, but in general it's a bad idea because people like us exploit these. So we're going to try the environment variable plus NOP sled combination to get to exploit this. So I think I already have the shellcode set in the environment variable. No, so these are the environment variables, but there's no shellcode here. So I have the commands here, and so this is the first command which I already run, which basically turns on ASLR, which is address space layout randomization. So you can even turn it off, but we're seeing what to do when it's turned on, when the binary will change location every time you run it. So let's set up the environment, and what happened? Okay, so yeah, so the shellcode got exported. So export sends things to the environment. So we check the environment variables again, and this thing is these values you can't read, non-printable characters. This is our shellcode, and you see we have /bin/sh at the end in some order. So yeah, the next command is, now we have to run. I'll show you C code for the binary first. So the C code, what it does, it takes an argument, and that argument is written as copied onto the buff, which is actually 100 bytes, and then basically it's just copied, it just prints something, and then it returns. So here you can see why we were avoiding null bytes inside our shellcode. That's because here the string copy will stop at the null byte and will not copy the rest of the string, which is not what we want. So since ASLR is enabled, we can't really get one specific address of where the environment variables of our shellcode is. So what we do is we run it multiple times. So this is some you can put some random 112 bytes here. This is just to fill up the buffer and add some extra thing for the eBPM stuff, and then you override the return address with the expected address of the shellcode. So you see here that the shellcode has 100,000 NOPs, which \x90, it represents an OP instruction, and then we have our shellcode. So if you land anywhere inside these 100,000 bytes, you're good to go. You have a lot of range basically to guess, but things move around a lot, so it's still hard to get it right. But now we are running it 100 times in a loop, so the probability increases a lot, to get one hit out of 100 tries. The probability of getting a hit increases. So let's try. So this initial address I got, this was an address from one of the executions, so it's expected that even when the binary is moved around, the movement is not a lot, because you're limited to 32 bytes of addresses, and that's how it's been implemented. So yeah, I just stopped it for a second. So I just wanted to show that we have the vulnerable binary we are running, and this dollar, what this is doing is generating an input. I'm generating the input using Python, and basically the input is A 112 times, and then this address, which you can see is written in Little Endian. So the actual address is FF, FE58 and EA. So the last byte is written first, and so we run this, and we're getting segmentation fault most of the time. We finally got a hit, and we are in a shell. Who am I? Root. So although our user ID is my user ID is still Akash, but my effective user ID is now root, because I was running a set UID binary, and now I basically have a root shell, and I can do anything with it. I can just do an rm minus rf / which is dangerous. I don't know why I wrote this here, but so now you basically have a shell. So we see the hit worked just 1 out of 100 times, but so that's one time is good enough. That's all for today. See you in the next video.